Hi, sometimes it's great to review the basics and to make sure that we get them right. There are two ways to think about multiplication, as a tool or as a foundation. As a tool, you assume that real numbers exist, and because of that you can use an operation called multiplication on them, and then you can describe the properties of that operation when you use it on the real numbers. You could describe it with 4 rocks. You put them in a square and you say, well, 2 times 2 equals 4. This is a simple example, but there are many ways to think of the properties of multiplication as a tool that links two factors x and y to the product z. The second way to think of multiplication is as a foundation, and it is a bit more advanced, it requires more theory, but basically it tells you that it is because of the properties of addition, multiplication, and ordering that real numbers are real numbers. So when you see something, you say, why is it a real number? Well, look at the multiplication that it has, look at the properties of it, look at the axioms that the multiplication, addition, and ordering ensures on this object. It is because of multiplication that numbers are defined. We are more used to think of multiplication as a tool, and we describe its properties with methods such as a table of multiplication learned by heart or more general analogies. But multiplication is also a foundation, and this is where we'll try to be at the end of the video, which is to be able to think of multiplication as a foundation of real numbers. To get a first general understanding of multiplication, we'll go through a usual construction of real numbers with Dedekind cuts. We'll see where multiplication fits in that system, what it does, and it will help us get a first idea of what is multiplication in a general sense. So this line represents real numbers, but you have to model what it is, and in the usual construction of real numbers, you go from the natural numbers to the rational numbers to the real numbers using the Dedekind cuts. Once we have a unit, the natural numbers are represented by the fact that we can join the unit to itself to get the number 2, number 3, and so forth. To get the number 2 on the line, you add 1 2 times, like this, and it's the same principle that you will use to multiply any natural number by 2. You will add them twice, just as you added the unit twice. N times m is represented by the fact that you are joining the extension of the number n, m times, and that's how you get a sense of multiplication on the natural numbers. Rational numbers are all the numbers that can be written as p over q, where p and q are integers and q must be different from 0. Examples of rational numbers are 1/2, 2/3, and so forth. To think of a rational number on the line, we divide the unit in q equal parts. It defines a grid. Q allows you to define a grid on the real line with steps as small as you want, and with p you can go anywhere on that grid as close as you want from plus infinity or minus infinity. To multiply p over q with p prime over q prime, you just need to multiply p with p prime and put that on the top, and multiply q times q prime and put that at the bottom. The way to naturally understand rational number multiplication on the line is if you have a rational number p over q, you just divide this by q prime equal parts, and then you will take p prime step on this new grid to get to the multiplication of p over q times p prime over q prime. It is more natural because to identify or reach p over q, you do the same thing with the unit. You divide the unit with q equal parts and you take p step on that grid to reach p over q. Let us now look at real numbers, which are not only rational numbers, but also irrational numbers such as the square root of 2, which cannot be written as integer p over an integer q. First of all, irrational numbers such as the square root of 2 belong on the real line because they have a precise interpretation as a length in some mathematical setup. If you build a square whose side is the unit, the diagonal of the square will be the square root of 2. So it is a length. Square root of 2 belongs on the real line, which in other things describes all possible length. How can we talk about square root of 2 if it cannot be written as a rational number p over q? Dedekind tell us that any real number is a set of rational numbers containing all the lower rational numbers. These sets allow you to talk about real numbers because each real number x can be uniquely described with a set of all rational numbers that are below x. X is the least upper boundary or supremum of that set. Because of this relationship, you can talk about the real number x without any reference to x directly, but only with reference to the set of rational numbers. This link between rational numbers and real numbers is chosen because it preserves multiplicative, additive, and ordering properties. We now know how to think of every number on the real line, even numbers such as the square root of 2. To think of square root of 2, we think of all the rational numbers that are below it. To think of integers such as 2, we think as well of all rational numbers below it. What does it mean for multiplication? Let's multiply square root of 2 with 2. Again, square root of 2 points to the set of rational numbers that are below it. So rational numbers such as p over q here will belong to the square root of 2. P over q also belongs to 2 because it is below 2. On the other hand, p prime over q prime only belongs to 2 and not to square root of 2 because it is above square root of 2. If you follow exactly the logic as described in the construction of real numbers with Dedekind cuts, you would multiply p over q times p prime over q prime, which you know how to do because they are both rational numbers. And you would do that for all p over q belonging to square root of 2 and for all p prime over q prime belonging to 2. Once you do all those multiplications, the set that you get is a set of rational number square root of 2 times 2, also interpreted as a thing that is below the supremum 2 times square root of 2. For the integers, to reach the number n, you added n times the unit. To multiply any number m by n, you're just adding n times the length of the number m, and you get the location of m times n. With rational numbers, you had two integers p and q that could be used to describe an instruction to go from the unit to the rational number. So q is used to divide the unit in q equal parts, and p is used to add or join the extensions p times. To multiply two rational numbers, you just had to reapply the instruction of the second one to the length of the first one to get to the product p over q times p prime over q prime. Same for real numbers. Instead of having two integers p and q for the rational numbers, here you have an infinite set of rational numbers that are below your real number, and you reach your real number by building the set of rational numbers with instruction from the unit, and then you take the supremum of that and you reach your real number, for example, square root of 2. If you want another number to be multiplied by this number, instead of building your set of rational numbers from the unit, you build them from the length of the number you want to be multiplied. The product is then located as the supremum of the set of rational numbers that you've just built. The basic principle of multiplication is the same for the integers, the rational numbers, and the real numbers. There's just a complexity going from adding n times to doing some dividing in equal parts and adding, or using a set of rational numbers and going to the supremum of that. But every time, the basic principle is that you identify or reach a number based on the unit, and to multiply, you actually use the same set of instructions, but you apply them to the length of the number you want to be multiplied. Are we happy with the multiplication that we got? So now we have a consolidated way to think of all cases of multiplication across the real line. However, there are three main problems. The first problem is that the multiplication that we got is logically indirect. When we think of foundational multiplicative properties of real numbers, we think of properties such as commutativity, the factors can change, distributivity, addition is distributed by multiplication, the existence of an inverse, you can find a number such that 1 times the other equals the unit 1. So these properties are something that exists with multiplication, but you will often have to take out a piece of paper and prove it, which means it's not directly there, it is logically indirect. You cannot see directly the foundational property of multiplication. So This is logically indirect, and it's something that we don't want. We want to be able to directly think of the foundational multiplicative properties of real numbers when we're thinking of real numbers and their multiplication. The second problem with the multiplication that we got is that it is geometrically indirect. When we're talking about the square root of 2, we want to directly talk about this point or this real number here, but instead of that, we're referencing the full set of rational numbers that are below the square root of 2. It is geometrically indirect because the set of rational numbers is also representable and located on the line, and when we are referencing it, we are really talking about the supremum of it, about the least upper bound of it, square root of 2 for example, and this point here is what we would like to directly talk about. The third problem with the multiplication that we got is that it has a terrible sign management. To simplify, we only took positive numbers, but this is what we need to have this nice expression of multiplication on Dedekind cuts. We want a theory of multiplication that works for 100% of the cases. Because the Dedekind cuts multiplication only works for positive numbers, it works for 1/4 of the cases. We need much better sign management and sign integration in our theory to have a great understanding of multiplication. We are not happy with the Dedekind cuts multiplication because it is logically indirect, it is geometrically indirect, and it has terrible sign management. Let us now review another kind of multiplication. It involves two lines intersecting at the origin, and it allows you to multiply any 2 points on the first line and get the product on the first line as well. And what is good about this multiplication is that, first of all, it's very concise, and concise is good because, addition, multiplication, ordering, they are defined as things. You shouldn't expect to require infinite sets of rational numbers to even understand what multiplication is in general. So concise is good, and also it solves an issue that we had, which is that to think, for example, of square root of 2 or multiplying square root of 2, we needed to think of every rational number below, so it was geometrically indirect, and now in this multiplication it's geometrically direct in some sense, because to think of square root of 2, you think of the point, and you can multiply this point directly with another point on the line. The way it works is that if you want to multiply any two numbers, for example, square root of 2 and y, then you would build two pairs of parallel lines, and you would take the first pair going from the unit and square root of 2, and one of the number you want to multiply with the other. Then you stop where you intersect with the line going from 0, and then you build the pairs of parallel line, and the one that comes from the unit, you put it such that it goes to y, and the other number that you want to multiply. And then when you build a parallel line to that, what you reach is the multiplication of the two. The way it works is that you have the ratio between square root of 2 and 1, and you can preserve it with parallel lines, and when you do this construction, the ratio reoccurs, but between y and another number, which is square root of 2 times y. Compared to the understanding of multiplication that we had with Dedekind cuts, this multiplication appears almost magical, but it actually raises one big question. With the axiomatic definition of numbers, the assumption is that you have an additive multiplicative with ordering manifold, and when you embed two constants, 0 and 1, inside it, then you get, because of the generative properties and the restrictive properties, you get the real numbers. With this definition, multiplication is at the core of what a real number is, and real numbers will not be defined without multiplication. In our case, however, multiplication seems to be defined after the fact. Real numbers seem to be defined as points on the line, and once it is defined, you can freely create another line intersecting at the origin, and you can multiply any 2 points on the line, enabling multiplication between real numbers. So which is it? Are the axioms right about real numbers where multiplication will be at the foundation of them, or is the line right about real numbers where multiplication will be only after the fact and optional? And it would really change how we think of real numbers and about multiplication. There's actually a reason to think that the axioms are right and multiplication is really at the core of real numbers. The reason is that even though the line seems to be this perfect and fixed object, capturing all the information of what real numbers are without any reference to multiplication, it actually depends on the unit, and there's something multiplicative about that. Any line depends on the choice of a length, which is its scale or the length of the unit. The scale can be any arbitrary non-zero length, and the length is what is used to define all the numbers. As a result, any careful understanding of the real number line will understand the line as a multiplication of itself. So there is actually a baby multiplicative manifold even in the apparent perfect and fixed line where we didn't see any multiplication before. The line can easily be misleading because it makes you forget that you chose the unit length, and so the multiplicative identity. It makes you forget that the choice is arbitrary, and so that the line is scale invariant, and so a multiplication of itself. It also restricts this multiplication to a very narrow manifold, because if you want to multiply again, you need to escape the line and then do some tricks and then find the multiplication. Numbers should not be conceived in such a narrow multiplicative manifold, but with a full-grown multiplicative manifold and together with its properties. And so the line is really misleading, but there's obviously something very good about it. The line does something very good. What it does is that it puts numbers into space, which is an additive manifold, and as a result there is no redundancy of information. There's not an additive aspect and a multiplicative aspect. There's only one clean information about numbers, the additive information, and it makes a very clear, clean object. Unfortunately, the price of that is that you forget about multiplication, you restructure it, and you restrict it. So it's a good aspect of numbers, but it's not the general aspect of numbers. It's not the right aspect. It's not the aspect that will help us understand multiplication and real numbers in a general sense. As discussed, we like the notion of points in space, but it is very easily attacked. For example, let's pretend for a second that the number 2 is represented by this point here. Just by changing the unit and drawing another line, we can see that number 2 escapes its first point and arrives here. Therefore, the first point that we considered was not capturing what it means to be the number 2. The usual resolution of this situation is to say that you choose a unit at the beginning, and so the number 2 can only be at this point because there's not this unit and this unit as well. If you want to talk about multiplication, about the full scope of real numbers, fixing the unit at the beginning might not be the best idea, because as we've seen with Dedekind cuts, multiplication was achieved by chaining the units and by having instructions from different kind of units. Same situation here. At first glance, these two lines appear to be in their own respective spaces without any communication, because we are not used to make any bridge between them. But if you do make a bridge between those two lines, then you get some meaningful mathematical pattern appear. If you make this point here match the unit of this line here, and if you actually make a bridge to make them fully communicate, then what do you get? First of all, the relationship between 1 and 2 that existed between this point here and this point here does now exist between this point and this point. It is now a relationship that crosses the space between the two lines, and so it's a bit of a different relationship, an arrow that crosses the two lines, and it is a relationship that is characteristic of the number 2. Second, the length that you find here is twice the length that you find here, and so it corresponds to the number 4. If you assume that everything is connected and embedded in the same space, then you don't need those arrows translating the information, and you can just read everything on this line as well. And there you have it, the multiplicative aspect of numbers, because it is clear that 2 times 2 equals 4. It is clear that multiplication by 2 is what this arrow represents, and the situations gets more general, where you can have any kind of multiplication arrow just by choosing and chaining the right units, using that dimension and that aspect of numbers. We want a multiplicative and additive manifold, and now we have an additive aspect of numbers. We also have a multiplicative aspect, and we just have a few questions that are raised by this new situation. First of all, how do we think of this multiplicative aspect? Because for the additive aspect, we think of it as a length in sort of a very specific space, because it's like the Euclidean space, it's made infinite in our mind, it's a bit like the space that Kant described, so there's definitely a specific environment where we think of length, and so the additive aspect of numbers. We'd like to also understand how to think naturally of this multiplicative aspect of numbers as well. Second of all, we first thought that this point was pointing to the number 2, but then it became the number 4 because we linked it to sort of a layer above that was more fundamental. So the question is this really the number 2 as well, or will we rewrite it and then maybe we'll write that it is 4 and this will become 8 and so forth. So now that numbers can be relative to the layer above, to the units that you find above, how do we decide, or how do we fix the meaning of numbers, and how do we make sure that we actually know what this number is? First of all, to decide what this number is, we shouldn't ask any question to the origin, because the origin is happy with any kind of unit that you define that is outside of itself, let's say. So the origin has nothing to say about what this number is, and there's only the unit that decides what this number is. At first, we thought on this line that the unit was here and that this was number 2, but now, because of the layering and the bridge that we've made, this has become the number 2, and so this has become the number 2 as well. We cannot really say arbitrarily that something is a unit, so we couldn't just say, well, obviously this is the unit, because it could really change depending how you relate it to other layers. If you have at least 2 numbers on the layer, then the choice of the unit becomes arbitrary and depends on the layer above. So what you have to do to fix what the unit is and to give a precise meaning to the full chain of multiplication and addition is to actually come back to a layer where there's only one unquestionable thing, and this unquestionable thing will be the unit. Once the unit is defined like this, there are no more debates about where are the numbers. This is clearly 1, this is clearly 2, and this is clearly 4. There is also no debate about what the unit is, because even if you can draw a smaller or larger unit on your own whiteboard, the unit stays functionally defined in the system as that which is alone on the upper layer and that from which every other number comes out. Indeed, every number is now represented with its additive aspect, but also with its multiplicative aspect coming out of the unit, and you have both the additive relationship that 2 plus 2 equals 4, or that 2 times 2 equals 4. The multiplicative aspect of numbers act as scalings, and now is a good time to think how should we name it and how should we interpret it. The language that we will use to talk about the multiplicative aspect of numbers should be suitable to talk about multiplication, to talk also about the interaction of multiplication with the addition, which we interpret as space, and should also be suitable to talk about the general properties of multiplication, such as the invertibility. So when you have an arrow going somewhere, you can find another arrow going back to the unit, for example. So if it's 4, then the invert would be 1/4 or 0.25. Talking directly of the multiplicative aspects as scalings is a bit technical. It also usually involves the notion of 2 spaces that are already defined and a scaling between them. But here it's almost the other way around, where this space 2 is defined as such because there's a multiplicative aspect 2 going from the unit to it. Being technical, the language of scalings doesn't really make your life any easier. It also involves notions that interfere with what we're seeing here. Therefore, to talk about the multiplicative aspect of numbers, we'll try to not use directly the language of scalings. When Einstein talks about his general theory of relativity and curved spaces, he doesn't talk about scalings, he talks about temperature and how in some places the solids used to make this system of coordinate would get bigger because of the temperature and sometimes smaller, and so a jump from one coordinate to another might mean a bigger length depending on where you are. These analogies are the sort of languages that we're looking for to integrate the multiplicative aspect of numbers into a system, just as we integrate the additive aspect of number in the notion of space. Temperature refers directly to scaling, and so it's a good idea to try it out. Unfortunately, it doesn't really work. The reason is that it involves the notion of hot and cold, and it's not something that really exists. Hot would mean all the numbers that are greater than 1, cold would mean all the numbers that are below 1, and then invertibility means if you have scaled up because of hot temperature, you can find a cold temperature that brings you back, and if you have scaled down from the unit to a number below 1, then you can always find a temperature such as this temperature brings you back to the length of the unit 1. It adds things, it interferes with the essential properties of multiplication that we want to capture in our analogy, so it doesn't really work as a language to talk about multiplication. What we're looking for is a language that accounts for this notion of flow coming out of the unit, of different stages that numbers take as they multiply, a language that accounts for the properties of invertibility, which is coming back to the original stage, properties as well that accounts for the fact that multiplication distributes over addition and so over space, and for all of those properties actually a strong candidate, and this candidate is time. Time is an inviting language for all the different properties of multiplication I mentioned. Using the language of time would mean that time flows out of the unit, that times put numbers in different stages as they multiply, so as they go through different times. Going back to the original stage would mean that time is reversible, so it's not intuitive notion about time, but it is a notion that we can apply to time, and you can say it's a specificity of the time that we need to think about the multiplication of the real numbers. As well for distributivity, the fact that multiplication distributes over addition, if addition is space, would mean that time flows through space, and it's also an intuitive and inviting notion. Overall, the language of time is an inviting language to talk about the multiplication of the real numbers. It is so because it can get meaningfully specified so as to match the properties that you need to talk accurately about the real numbers and about the multiplication. It is also compatible with another very strong analogy of numbers, which is the analogy of space. The analogy of space is not only used to talk about the additive aspect of numbers, where adding two numbers is the same as joining two extensions in an Euclidean space. It's also used more generally to talk about numbers, such as when we say that a function converges between 2 points. So it is a very strong analogy, and it is very desirable that the language that we use is compatible with this very strong and widespread analogy, as well as compatible with the properties that we need to talk accurately about multiplication. For all of these reasons, the language of time is a language that we will use to talk about the multiplicative aspect of real numbers. What does it mean that numbers are now understood in a space-time manifold? Let's take the origin, for example. So the origin is this very peculiar singularity that additively is the neutral additive element. Therefore, when you add it does not add anything to the story, nothing changes. But when you consider it multiplicatively, it also has a very peculiar property, because whenever you multiply any number by 0, or if you multiply 0 by any other number, you come back to 0. Therefore, 0 is absorbing. And these properties let the original 0 be interpreted in a space-time manifold as a sort of peculiar black hole, because additively it is this sort of singularity somewhere, and multiplicatively it is absorbing anything into itself. So the language of space-time lets ourselves have both the additive and some multiplicative aspect of the number 0 in our representation of it, and so we can start to see the advantages of using it. What about the other numbers, such as the number 2 or the number 4? All the numbers now have two aspects that are connected. They have the multiplicative aspect coming from the unit to their additive aspect. So number 2 has the additive aspect here, and has the multiplicative aspect that go from the unit to the additive aspect. Same for number 4, it has an additive aspect, and it has the multiplicative aspect that go from the unit to the additive aspect of the number 4. And as we have seen, these aspects communicate and they can be reapplied. So the additive aspect of 2, so the space of 2, the extension 2, can be added to itself to get the number 4, so 2 plus 2 equals 4. And the multiplicative aspect of 2 as well can be reapplied, and so 2, and we get that 2 times 2 equal the multiplicative aspect 4, or the space 4 equivalently. So we can see that now the numbers of the two aspects, they also have the two dynamical aspects of numbers, where numbers can be adders or multipliers. In the space-time manifold, you also have the more general properties of addition and multiplication. So for addition, we already made a video covering the general properties of addition and how they are covered in the notion of space. But for time, it is the same thing. So we've already seen that, for example, the invertibility of multiplication is interpreted as the fact that time is reversible, and so you can come back to the first stage of the number. But you also have all the properties represented. For example, for addition, you know that you can add a series of numbers, and it doesn't matter if you rearrange them, either changing their place in the series or even changing how you compute them, like 2 by 2. And so you can have 1/2 plus 1/2 plus 1 plus 2 is the same as 1/2 plus 1 plus 1/2 plus 2. And you know that it is always the case. It is because of associativity and commutativity of addition. And you have the same thing in multiplication, where you can say, well, whenever you have a series of time, it doesn't matter how you rearrange them, because the end result, when you do the product of all the times, will be the same, even if you change them, change your order into series, or even change how you compute them by make some local computation for the first two terms, and then you multiply with the rest. It doesn't matter. So because of associativity and commutativity, the end result will be the same, and the end result will have, because it is in space-time, it will have both the time aspect, the multiplicative aspect of the number, and the space aspect, the additive aspect of the numbers. There's one number that is a bit more difficult, and it is the unit. And the unit is the only number that exists in the upper layer. And because of that, we say the seed of space-time, because every other number has a time that comes out of it. But it is also found as a concrete number inside the space-time manifold, a number that you can multiply, that you can add freely. Therefore, the unit has sort of this dual aspect. And it's not something that we understand clearly right now, but it is something that we will try to understand more as we move forward. We have many reasons to be satisfied with the language of spacetime that we just built to talk about real numbers. First of all, it involves a full-grown multiplicative manifold. When you multiply, you can multiply again. It also involves a geometrically direct interpretation of numbers. When we talk about the number 2, we talk directly about this point, although maybe about the time that goes from the unit to this point. But it is geometrically direct. It would be the same thing for example, for the square root of 2, which we had trouble to find a direct interpretation with the Dedekind cuts, for example. It is also logically direct, which means that we can talk about the general properties of addition and multiplication right in the manifold of spacetime that we use to understand those numbers. Invertibility of multiplications means the reversibility of time, and so forth. There is still one reason why we are not happy yet with this manifold that we just built, and this reason is the handling of the signs. So far we have understood space as a manifold in which we can join extensions additively, and time as a manifold in which we can scale a length into another length. And these notions work for positive numbers, but if you talk about the full scope of real numbers, you also have the signs that change how multiplication works or how addition works, because you can have some sign that change, or you can have a different kind of additions occurring. And so we need to be careful about how we understand the signs to fully understand the real numbers. There are three signs: the positive, plus, the negative, minus, and the sign of zero that we know plus, minus. When we multiply two numbers, their signs multiply as such. Plus times plus equals plus, plus times minus equals minus, minus times minus equals plus, and plus minus times any signs equals plus minus. When you add two numbers, the signs act as sort of polar opposites. So if you add two numbers with the same signs, the sign of the sum doesn't change. But if you add a positive number and a negative number, then if the positive number is bigger, then the positive sign prevails and the sign of the sum is the sign plus. But if it's the other way around, then the sign of the sum will be the sign minus. And if the positive and the negative are exactly equal, then the sign of the sum will be the sign of the result 0, and so plus minus. If you need more detail about how the signs change addition and our interpretation of space, then feel free to check the video about the addition of the real numbers. In practice, the signs are not a big deal, because if you're looking at products, then you're looking if there is an even number of -1 factors in the product. In that case, the product is of sign plus. If there's an odd number of -1 factors in the product, then the sign is minus. And for addition, you just use a sign to say that if you add two opposite quantities, then the sums cancels out. We now have to understand the signs in a way that is compatible with algebra, but also with the language of spacetime that we use to understand real numbers, including the fact that the seed of spacetime, or at least its image, has the sign plus. All the while, we shouldn't go too far away from the mathematical practice of sign, where multiplicatively we just check if there is a change of sign, and additively we just cancel out quantities in our mathematical expressions. The multiplicative algebra of signs tells us that signs are a bit like different teams and the act of belonging to them. The additive algebra of signs tells us that signs are a bit like polar opposites, And there's also a notion of gradation, because you can sort of have partial wins. If plus prevails, maybe it's a bit smaller than what it used to because it's got added to negative. If you forget about this gradation, and if you say, for example, I want to say that team is truth, lie, and you say the act of telling the truth, the act of lying, then you can say that telling the truth about truth is truth, telling the truth about lie is a lie, telling a lie about a lie is truth, and maybe being unsure if it's a lie or truth leaves you uncertain. So you can have this match, but then when you look at the additive aspect and you say that you can have partial win between truth and lie, then it doesn't really match, because truth and lie is more in the absolute range, while we need gradations. There are many ways to define different teams that are polar opposite, but that also have some sort of gradations. For example, if you say that plus is love, minus is hate, and plus minus is indifference, and if you have the active part of that, of loving, hating, or being indifferent about something, then you can say that loving love is love, and loving hate is hate, and hating hate is love, and being indifferent about love, hate, or indifference is still indifference. And it also matches for the additive aspect, where you can have that love and hate are opposite, and maybe love triumphs because it is bigger than hate. But now the question you want to ask is, does it match the notion that maybe the seed of space-time has also the property of love, and maybe you can think it's a nice idea, but then does it also match the mathematical practice of where we just check if there's a change of sign, or where we cancel expressions? In the case of the interpretation of signs as love, hate, or indifference, it matches the algebra of signs that we need. It maybe creatively matches the space-time manifold that we're using to describe the real numbers, with also the seed of space-time that would now have the property of love. But it is maybe a charged language with regard to the mathematical practice, where we're just checking if there is a change of polarity or cancelling quantities. And so there is a case to be made to be as neutral as possible. The most neutral language to talk about polar opposite teams might be the language of logic, with truth and falsity, but as we've seen, it doesn't really work, because we also need gradation. The next most neutral and maybe universal language that defines opposite teams as well as gradation might be the language of morality. In the language of morality, the interpretation would be that plus is good, minus is evil, and plus minus is maybe a throwaway state, and the active part of that would be the preservation or the inhibition or changing team. And so you have preserving good is good, and preserving evil is evil, and inhibiting evil is good. And you also have this gradation possible where you can have a greater good or lesser evil, so it would also work for the gradation part. For the language of space-time, what it would mean is that you would have time that preserve or time that change the team you belong to, and you have space with a moral element embedded in them, and that can reach a greater good or lesser evil or greater evil. Since the language of morality transfers back to the seed of our space-time manifold, attributing it the property of being good, then the language of morality becomes the language of theology or teleology. In conclusion, how should we think about the multiplication of the real numbers? To answer that question, let's first answer the question, what are we talking about here? What kind of numbers are we talking about? And to have numbers, we need a syntax that can be configured and that can be recognized, and so we need a big package. We need logic, we need consciousness, we need telesis, and so we need the cognitive theoretic model of the universe of Christopher Langan. Then we also need an object defined as real numbers, and so we need the axioms of real numbers of David Hilbert. And these are the axioms that we have tried to integrate into the language that we use to talk about real numbers. Then our position is that there exists a privileged syntax to talk about real numbers. This syntax involves the infinite space syntax of Kant, but this syntax is mostly additive, and so it was lacking what is required to talk about multiplication and about real numbers in general. So we developed a time and theology syntax in this video to fully talk about the axioms of real numbers in the language that combine them in something that also involves the infinite space syntax, and so in language that would be a privileged syntax to talk about real numbers. In the syntax, numbers are a point in a space-time and teleology manifold. In this manifold, what is multiplication? Multiplication is the time aspect of numbers. So each number has a time aspect and a space aspect, and multiplication is a time aspect, and you can go further. You can multiply again. You can talk about the general properties of multiplication. For example, invertibility is time reversible. You can talk about the associativity of time, of commutativity. So it's a very rich manifold, a full-grown multiplicative manifold where you can talk about multiplication through the language of time. And what is interesting about this representation is that also it is quite reflexive, because we are ourselves in a space-time and theology manifold, and so there are some properties that get transferred and that explain some of the things that remain a bit unexplained in our model. For example, there used to be a unit that is sort of alone in the upper layer that had two aspects, and now we understand, since we have this reflective language, and since this upper layer above is sort of the seat of space-time and theology, then we understand it as the global operator descriptor of God. And so in our syntax, the interpretation is that this is where God created the space-time and theology manifold in our syntax, and then we can explore this syntax that is accurately describing the numbers to just think about numbers in general. So there are still a few questions about the space-time and theology manifold. For example, what is these zeros that behaves a bit like a black hole? When you multiply anything by zero, it absorbs it into itself. Or what is this number one that is the image of what we understand as God? Does it mean that there is such a thing as a perfect man or Jesus? And these are questions that remain, but overall we have a space-time and theology manifold that matches the axioms of real numbers, which means their definition, and multiplication can be understood as the time aspect of this space-time and theology manifold, where numbers are defined as points in a space-time and theology manifold.